Hi everyone. So this is a supplement to lecture 3 on unit conversions and data types, and I'm going to step through the examples here on this example here on unit conversions in Excel, and then after I'm done with this, I'll move over and do the example for the Python on data types. So let's just look through this example here real quick. So this is an equation we're going to try and calculate using the given units. And this is the friction factor is an important quantity in fluid mechanics that can be used to calculate the pressure that a fluid loses while flowing in a pipe. One equation for the friction factor is this equation here, where rho is the density, v is the velocity, d is the diameter. And so the questions are, what are the units of f if this equation is going to be dimensionally consistent? So we talked about dimensional homogeneity, where we said that the left-hand side must equal the right-hand side. And so let's think about that for a minute. What should the units be? So I can actually, let me just pull up a little notepad to have somewhere to scribble down, and I'll grab my pen real quick. Should have done this beforehand. Sorry for that. Forgot about this part. Okay, so if I have, this is just a number, right? And so it's really what's in this quantity here to the minus 1/4. So let me see what that is. So I have rho, which looks like this, v d divided by mu, all right? And what units are those going to be? So rho, that's in pounds mass per foot cubed. So now I can, without converting the number, I know that I'm going to put everything in SI units just to make my life a little easier on this particular dimensional consistency thing. So I'll say that's going to be the same as kilograms per meters cubed. That's from, mass and a length cubed. Then V, that's miles per hour. Well, that's going to be the same thing as a length per time. So a length is meters and a time is seconds. Okay, so that's from the velocity. D, that's 3 inches. That's also a length. That's meters. And the last one, mu, this is called a viscosity, and it has kilograms per meter second. Well, that one's pretty convenient. Kilograms per meter second. So now let me check what I have going on. So, excuse me, I did that wrong. That's in the denominator. I was just staring at that thinking that's not going to work out right. I need to flip that guy upside down. This is going to be kilograms per meter second because I'm dividing by mu. All right, now that looks like the answer that I was going to expect. To do that, I'm going to have kilograms cancels with kilograms. 1, 2, 3 meters cancels with meters cubed, and seconds cancels with seconds, so that is unitless. Okay, so this has no dimensions. That tells me that when I have no units to the minus 1/4, that's also no units. That means F must also have no units. And that's true. We're going to find out about these numbers in fluid mechanics, which are called dimensionless numbers. Okay, dimensionless numbers. A little preview for what you're going to do in transport and heat mass transfer and all these other classes. Okay, so that's what we're going to get there. So that's the answer to A right there. Okay, so now let's move on to B. Let's go ahead and do our unit conversion. So I can drop my notepad, put that guy away. All right. And what do I got going on? Okay, so now it says calculate the friction factor and convert it and print it to the screen. So let me type in here. I have rho, I have v, d, and mu. Okay, and let me put them in the units that they were given in. So here I have 62.3. I'm going to put pounds mass per foot cubed. And then I have 35 miles per hour, and then 3 inches, and 1.02 times 10 to the minus 3. There's a little convenient thing. You can just put an E when you write that, 1.02 e minus 3, that'll do times 10 to the minus 3, and this is kilograms per meters times seconds. Okay? So now what I'm going to do first is convert them all to SI units. So SI units will make it kilograms per meters cubed. Kilograms per meter cubed, that's what I want there. And I want this one in meters per second. This one I want in meters, and this one will be the same, right? That'll make my life easier. I guess I put the apostrophe in front of all those, but it's shown up on this guy. So I'm going to take them off real quick. That's bugging me. I'm actually not using Excel for this particular video, but it's the same. I'm using the OpenOffice version, which is called Calc, and apparently it shows the apostrophe. Okay, so this one is the same. Okay, this one will be easy. That'll be right there. I'll make that one equal. Okay, so now I need kilograms to pound mass, feet cubed, meters cubed, etc. So I'm going to pull up my, I have to show the guts going on here, but let me pull back out my units handout. Now I told you before that I expect you to have these memorized, but I'm doing this late at night and I don't want to make a mistake on the video. So I'm going to go ahead and cheat a little bit. But this is a good opportunity to see if you remember these, all right? And it's good practice. So let's see, I have 62.3 pounds mass. So I'm going to be converting from pounds mass to kilograms. Well, pounds to kilograms, I should need to divide by 2.0246. Excuse me, 2.2046. So 2.2 pounds per kilogram. So I'm going to divide by 2.2 there. And then for, I have feet cubed in the denominator. So now I come down here and look where our feet, well, I have 3.3 about feet per meters. So let's make sure we do that right. If I have feet in the denominator, I'm going to need feet in the I'm going to need 3.3 in the numerator. So I'm going to multiply by 3.2808 cubed to get that guy. All right? And so that gives me a density of around almost 1,000 kilograms per meter cubed. Okay, now 35 miles an hour to meters per second. So this one, so I have miles, and I don't think I have miles on the sheet, so it's not one you need to memorize. You can look it up, but I happen to know what miles is to feet. A mile is 5,280 feet, okay? And then I know that a foot is that many meters. So now feet is in the numerator, so I want to put that in the denominator. So I divide by 3.2808. That will give me meters. All right, and now I need to get rid of the hours, and I have 3,600 seconds in an hour. I need to put hours in let's see, it's per hour. So you put hours in the numerator, which means 3,600 in the denominator, and that gives me 15.6465 meters per second. Okay, the last one is inches. So 3 inches, I have to get divide by 12 to put it in feet, and then I need feet to be in the numerator, so I multiply by 3.2808 feet per meters, and that gives me that seems wrong. Let's see, 3 inches, I have to divide. I want meters in the numerator, excuse me, not feet. So I have to divide by 3.2808, and that gives me 0.076 meters, and then that I have in view. Okay, so now I want to calculate the product of these. So the product, which I'll tell you in fluid mechanics is a number called the Reynolds number, as rho times V times D times mu. Okay, now look at that. It has what units? Well, we already did that in our previous one. It has no units. That makes our life easy. And now we can calculate F, which is that guy to the minus 1 over 4 multiplied by 0.0791. And that gives us our final value. That's our final answer. All right, so we have a key included. We can check and see if we were right. And let's double check and see. Did we get 97.92? Yep. Did we get 15.65? Yep. Did we get 0.0762? Yep. And then we have 1.023. Yep. And then the value of f, looks like we have a mistake. Let's go back and see what we did wrong. Did I type something in wrong? 0.0791 times rho VD. Oh, I know what I did wrong. I did rho VD times mu. It should be divided by mu. There we go. Now we get 0.0024. Now look over here, 0.0024. Perfect. Okay. Now you notice on the key here, I won't take the time to work through this example here, but it also has English units. And the nice thing about doing this guy is once we, to follow the tips, remember these tips I told you from the lecture, I said convert at the beginning and convert them all to kilograms and meters and seconds or slugs and feet and seconds. So the nice thing is once I did that conversion to kilograms, meters, and seconds, I can just do the multiplication and I don't have to worry about getting rid of these intermediate values, right? Intermediate units that are funky. They'll all just cancel. And the same thing happens if I do slugs and put the slugs in here. I don't have to worry about whether I have force, that comes into that calculation. Now this one happens to be relatively easy because I did it with, it's a unitless number, but I think it's a good exercise for you to go through and do the English units for yourself. So do the English units right here and get this one in, slugs per feet cubed, right, etc. Hint, hint, that's just going to be, this factor of 32 where you want slugs in the numerator, so you're going to divide by that guy, right? It's going to give you, around 2 slugs, okay? So play around with that. See if you can do it without looking at the numbers on the key. Try and follow this process here of doing it and try to get that answer out for yourself. Okay, so that's all I'm going to do for this first example. If you're watching the lecture, you can go ahead and pause this video and go back to the lecture and learn about data types and error, and then you can come look at the Python example. For those of you that want to go straight to the Python example, here we go. Okay. So the Python example here, remember I said that there were these different types of data types, different ways in which we store numbers on computers. So I said there's Boolean values, there's integer values, there's strings, and there's floating point values. And so the Boolean value, if I want to store a value that's Boolean in Python, I just take a variable and assign it to be a value of true or false. Okay, so this is pretty straightforward. I can also convert from 0 and 1 to a Boolean value. So a 0 would be a false and a 1 would be a true. So if I run the thing up to here, let me see if this does, if I can run this in pieces. Let me see. Let's see. Source. I used to know how to do this. Add a block comment. Oh, I don't care to do that. All right, we'll just run it from here. See what happens. Okay, we'll ignore all the stuff below. Ignore everything, integers on below down here for a second. So this says print Boolean, and this says, Boolean 1 is equal to true, and then I said not bool 1, that's false. So those are 2 values, and it prints out true and false. And then it says I can convert from that to that. So if I convert a 0, it gives me a false, and I convert a 1, it gives me a true. Okay? So the practice here is what happens when I convert a floating point number to a bool. So let's try that. Let's print bool of 0.2 and see what happens. So I can run that, save it, and run it. And what does that do? It prints a true. Okay? So I put an 0.2 in, and it made that guy into a true. What happens if I make it a point, like a 0? That one turned it into a false. So it's pretty nice to me. But you need to be careful about this, because what if I did 1 times 10 to the negative 14? That's pretty close to 0, and that is giving me a true. But what happens if I put in 1 times 10 to the negative 18? We'll see if it's nice about this. Ooh, it still gives me a true. I bet if I pick a really small number, like minus 400, it will resolve as a false. Okay? So you need to be careful with the floating point values. It's basically going to give you a true for anything not 0, but if you get really, really small, it's going to mess up. Okay, now let's move on and talk about integers. So integers here, I have int 1 is 3 and int 2 is a 4. And notice that when I do subtraction with integers, I get exact values. So let me go actually come down here, since none of this is important, and comment it out so it stops messing us up. We'll do that to make our life easier. Comment with a control 1 and a control 1. Do that here with these guys too, control 1. Okay, sorry about that. All right, so now what happens here? So I do int 1 minus int 2. That should give me 3 minus 4 should be negative 1. And I can look, does it exactly equal minus 1? And I get, yes, it does. That 3 minus 4 comparison operator minus 1 is true. Okay? So that's to tell you that integer arithmetic is exact because I'm just doing this Boolean subtraction. We'll see that it's different with floating point arithmetic. Remember, we talked about that with errors. Look here, I can, using this module we'll talk about later, I can find what my maximum integer size is in Python. It prints out to be this really large number. Let's see how many does 3, 6, 9, 12, 15, 18, I get 19, something times 10 to the 19. That's a pretty big value for an integer. I can also convert other values to integers. So look here, I can convert a string, a character of 3 into an integer, and then if I print that out, I can take away the plus 2 there. That will give me an integer 3. And then I can do things like, addition to it, okay, which gives me a 5. What happens if I just tried to add the string 3 and a 2? This gives me an error. It says must be a string, not an integer. It doesn't like that I'm trying to add an integer to a string, okay? So this is important. Note that when I get errors like this, I look at what it's telling me the error. That's telling me what's going on. So it's really important. Look, too, this tells me the line. It says on line 48, you're printing this, and it says you have this error. So that's a little hint. When you get an error, read the line, the last line, and it tells you usually where the error is, or at least a clue of where to go look. Okay, so this is kind of like dimensional homogeneity, right? I can't add strings and integers. It doesn't like that. But if I convert in 3, okay, that it will be fine with. Notice that when I convert a floating point value, a decimal, to an integer, what happens here? When I print int 4, let's look at that one again, it prints out a 4. It rounds that number down. So it turns out I always round down. That's called truncation, okay? So no matter what number I put in here, if I make it 4.9999999, okay, that is going to round down to 4. Be really careful. If I put too many 9s here, it might mess up. Let's see what it does. It actually gives me a 5. So if I do too many 9s so that I exceed, the finite precision of my decimal, this is actually rounded it all the way up to 5. But that's undefined behavior. It won't always do that. I don't know if I run it every time if it'll give me 5. It looks like it does. But that's kind of interesting. But usually it'll just round down. Okay, it's wanting to round it down. All right, so that's enough for integers. Let's comment that out, and we can actually this has practice. So what happens when you subtract two really big integers? So let's do this. sys.max size minus 10. I'll make that int 1. and I'll make int 2 equal to sys.max size minus 9. So let's just print those and see. Let me print int 1, int 2, just to see what happens. Okay, when I do that, I get these really big numbers, right? Blah, 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 97, blah, 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 98. Okay, so now let me do print int 1 minus int 2. And what does that give me? It gives me minus 1. Look at that. It does exact subtraction. Whew, that's pretty nice. Okay, so integers don't have the problem of round off error because it's not a floating point value. Okay, that's what we're seeing there. Now I can comment those guys out. Let's come down and look at strings here for a minute. Strings, okay, in Python are defined using either double or single quotes. Okay, I can use either. So I can have the quick brown fox jumped over the lazy dog, okay, or Mary had a little lamb. All right, both of those are strings, and if I go to print them out, I go to run that thing, it prints them out. Okay, spaces and all. Spaces have a character in the Unicode table. So you can convert numbers into strings and strings into numbers. Okay, so here we did that already. I want to convert 3 into a string, so I run that guy, and what does it do? It converts. I can just print string 3, and what happens? It converts it into 3. Okay, it's hard to tell the difference, but if I go ahead and do +4, this plus now, when it's using strings, it doesn't interpret that as add. It interprets that as put next to. So, or what it's called concatenation. That's this word like this, concatenation. Okay, so it sets them right next to each other and makes a string of those two things together, and it makes 34. So in Python, you can have 3 plus 4 equals 34. All right, but that plus now here is not the same as an addition for integers. It is a concatenation operator, okay, for strings. You can also go backwards. You can take 3.4, or backwards. You can take floating point values and also convert them into strings. And if you look at what that does, now it's a 3.4. And if I add something like a 5 onto it, what is that going to give me? That's going to give me 3.45. All right, so again, this is just, it just turns this into the characters, 3.4. That's what's going on here. All right, I don't think there were any other things to say about that. Let's take our last look here at floats. So floats are numbers with decimal points. To make sure that you get a float, you need to put a decimal point after the number. Okay, so if I put just a 3, it'll give me an integer. But if I put a 3 point, now it'll make sure it defines that as a decimal number. Right? I can also give it a decimal number by using scientific notation or exponential notation. Just like in Excel, if I put an E, it'll treat that as a times 10 to the, right? So anywhere you see an E, you should think times 10 to the exponent 1. It's just more convenient than writing times 10 to the. So this will give me 30. Okay, I could do 3E0, and this will give me, float 1 and 2. All right, let's see, floats, I can print both of those guys out. Print float 1, float 2. And it'll print out 3.0. Notice if I take the decimal point off, what happens? It prints out 3, not 3.0. This is Python's way of telling me, hey, that's an integer, not a float when you print it out. Okay? So what are the minimum and maximum values of a float? I'm going to comment this out as we go along. We can look up again on that sys, and that tells me that my minimum and maximum value, look, there you go. The maximum value is 1.7 whatever times 10 to the 308, and the max exponent is 1024. Can't have a bigger exponent than that. That would be 2 to the 24, I think. So the max 10 exponent is 308. The minimum exponent is minus 307. this gives you 15 digits of precision. So I said 16 is a little off, only 15 digits of precision. All right, so that tells you what it is in Python for double. So what happens when I add a float and an integer? So if I come over here, I have float 1. Up here I defined int 1. This wants this to be defined. I think I want a different int 1. This guy here. Okay, so if I run that, what happens? Oh, it doesn't like that I turned off sys import. Let me do that real quick. Okay, sorry for that scrolling around. Just trying to get down here. We'll turn off that. We'll comment that out so we just get what we want. Okay, so what happens when I add the 2? It turns it into a float. So if I add 3 and 3 from the integer, it turns it into a float at the end. So integers are kind of fragile. They get turned into decimals really easily. Okay, so I can turn those guys off here. What happens when I subtract 2 floats that should be equal? So I have 7/3, and this one should also be 7/3. What's going on here? Let's see what happens here. And look at this. This gives me a number that's not exactly 0. So subtraction and addition, for that matter, with decimals is not exact. Okay, this is giving me something slightly different. All right, finally, you can convert other data types. You can take an integer, use this float command to convert it to a float, or you convert a string to a float, and you can see what happens there. This one prints out 3, and this one prints out 6.2, right? Not 5.21 if it was treating it as a string. All right. Last thing is just to show you a little bit of what's going on with errors. So these are just some examples of different errors that we talked about here. So the first one is a truncation error. Well, actually, I think what I do here is I define a bunch of things. I don't know why I have this thing here. Let me delete that row. I define a bunch of numbers. And I'm going to come down here and let me uncomment this. Okay, so this is going to print, each of these print statements is going to print out 20 decimal places. But remember, there's only 15 or 16 or so. Okay, so this first one, it says float 2/3. So I'm going to print out, remember, truncation error is where I don't get, it should be 6666666 forever, but look, it messes it up. So I print 20, I print 2/3 out to 20 digits, and what happens? I lose decimals of precision. Now here, remember I said what happens? I have this really small number, 5 times 10 to the 400. If I print that out to 20 decimals of precision, this one, let's see what that looks like. I get 0. I get an underflow. And if I try and print out this really big number that's too big to hold, it gives me a value that's infinity. Okay? So that's my truncation, underflow, and overflow. Now let's look at the last 2 errors, the round off error by addition. So I'm going to take my big number 1 and my big number 2, and I'm going to add them together. Look, they're pretty much the same number, but they differ out here in the small value. But this is like times 10 to the 9th, right? So this would be like 1,000,002, or 1,000,000,02, or something like that. I'd have to count the number of zeros to tell exactly what that number is, right? So now I have my big number, and I have, it looks like big number 1, big number 2, and then I have the small number, which is really small. It's like 7 times 10 to the minus 9th. It's like 1/1000,000th or 7/1000,000ths. So now I take the big number and I add the small number, and what does it give me? It gives me exactly the same as the big number. So I added that small number in and it didn't do anything. So that's round off error due to addition. Now round off error due to subtraction. Let's look at that guy and what's going on here. I have my big number and my other big number, and I subtract them, and what happens? I should get just 1 times 10 to the minus 6, but look at all the other garbage I get out here where the computer has just pulled these things randomly from memory. Okay? So that's an example of round-off error. Okay, so now what happens when this says what happens when I add 0.1 together 10 times? Do I get exactly 1? So let me take a value. Let me take x equals 0, and then I'll do x plus equals 0.1. So this plus equals operation, that adds 0.1 into my x. So let me do it again. X plus equals 0.1. So I want to do that 10 times. So I have 2 of them there, so let me copy and paste that 5 times. So that's 4, 6, 8, 10. Okay, and then I'm going to print x. So let's watch what happens here. Look at that. I don't get exactly 1. I get something really, really close to 1. Again, floating point arithmetic is not exact. Even if I, but if I were to print 0.1 times 10, that is going to give me 1. Okay, so I could do that and subtract x from it, and look, I'm going to have some small error, 1 times 10 to the minus 16, that messed up a little bit, okay, a little bit of error. Okay, so these are some examples of data types in Python and finite precision in Python. I hope I've impressed upon you the relevant ideas, and I hope that this helps you with your homework. Okay, have a good one.